Hi there. So in this video we're going to look at a strong acid, strong base titration, and in particular we're going to look at the situation before the equivalence point. So if we were titrating the hydrobromic acid in the question provided, then we would be adding sodium hydroxide and we would not react all of the hydrobromic acid, therefore before the equivalence point. So in this particular question, we're asked to determine the pH when 20 milliliters of a 0.3 mole per liter solution of hydrobromic acid, which is HBr, is titrated with 40 milliliters of a 0.1 molar sodium hydroxide solution. Sodium hydroxide is NaOH. So the first step with any reaction equation is to actually write out the reaction and determine exactly what we're forming. So let's do that first. Okay, so one of the rules to remember is that strong acids and strong bases will completely ionize in water. Because we're working in solution, we can assume that we are in water and these two reactants will ionize completely. Therefore, we're going to undergo a double displacement reaction and form sodium bromide salt as well as water. So, given that we have a reaction equation, we can start by comparing the amount in moles of the acid and the base to determine which one is our limiting reactant. It's also important to note that because the acid and the base completely ionize, we're using a forward arrow to indicate that this reaction will go to completion. So, let's fill in our ICF table. Because we are in solution, there is an excess of water and we do not need to consider water in our ICF table. So I'm just going to cross it out. Now, we've been given the initial volume and the concentration of our hydrobromic acid. So in order to fill out the initial mole column, we're going to need to determine the number of moles we're working with. So you can see N represents moles of the hydrobromic acid, and I'm multiplying my initial concentration in moles per liter times my initial volume. However, my initial volume was provided in milliliters, and my concentration is in moles per liter. So I'll need to convert to liters by dividing the milliliters by 1,000 milliliters per liter. This way, milliliters cancel, and we're left with a volume in liters. When we complete this math, we get a final mole amount of 0.00600 moles. You can see that the concentration I'm provided has 3 significant digits. Furthermore, the volume I was provided also has 3 significant digits. Now, this value here, 1,000 milliliters per liter, is a conversion factor, and we can assume that it has an infinite number of significant digits. Therefore, when we divide a number with 3 significant digits by a value with infinite significant digits, we get 3 significant digits. We keep the lowest number. So 3 significant digits, 3 significant digits, and I've carried 3 significant digits, 600, into my mole amount. Now I'm also going to need to know the moles of sodium hydroxide in order to determine the limiting reactant. So let's solve for that as well. So I've repeated the same steps as in the previous example of finding the moles, and I've kept 3 significant digits. When I do the math here, I get a final molar amount of 0.00400 moles. Okay, now that I know how many moles of each reactant I have, I can put that into my ICF table. Given that hydrobromic acid and sodium hydroxide react in a 1-to-1 ratio, we can see that the limiting reactant is the sodium hydroxide. So my change in molar amounts will be equal to the total amount of sodium hydroxide in moles. And I have formed 0.004 moles of sodium bromide. That means that my final molar amounts will be 0.00200 moles of HBr, my hydrobromic acid, 0 moles of sodium hydroxide, they've all been reacted, and 0.00400 moles of sodium bromide. Now, the thing we have to think about is, does sodium bromide affect pH? Well, when sodium bromide dissociates, it will form sodium ions and bromide ions. However, because they both came from strong acid or strong base, they both have a negligible impact on pH. Or in other words, they won't remove a hydrogen ion from water to form hydroxide. Furthermore, they won't donate any hydrogen protons to form hydronium. So, the molar amount of the salt does not have to be considered when considering the pH in a strong acid, strong base titration. This is unlike a weak acid, strong base, or strong acid, weak base titration, where the salt will contain a conjugate acid or base which needs to be considered. Now that we know how many moles of hydrobromic acid we have remaining, we can determine how that will impact the pH of the solution. So, I'm going to write a new reaction where my remaining moles of hydrobromic acid react with water to form hydronium ions, which we can use to determine the pH of the system. Because we're in solution, my hydrobromic acid is aqueous, my hydronium ions are aqueous, as well as my bromide ions. However, water can be written in liquid form. I'm now going to fill in my new ICF table and determine how many moles of hydronium ion are produced. Because water is in excess, we do not need to consider its molar amounts, and I will cross it out. Furthermore, because the bromide ion does not have an effect on pH and will not accept a hydrogen proton from water, we can cross out it as well. We had 0.002 moles of hydrobromic acid remaining after titrating with sodium hydroxide, so that will be my initial mole value for hydrobromic acid. Initially, I have 0 moles of hydronium ion. Because the acid will react and go to completion, all moles of the acid will be utilized. Again, keep in mind that water is in excess, so it will not be the limiting reactant. Therefore, my final molar amounts of hydrobromic acid will be 0 moles, and my hydronium ion will be 0.00200 moles. Now that we know the number of moles of hydronium ion we've formed, we can determine its concentration. However, we must keep in mind that the volume has changed. Initially, we began with 20 milliliters, and we added 40 milliliters of sodium hydroxide. So let's take a look at our new volume. So this one's pretty easy to figure out. 40 milliliters plus 20 milliliters gives us 60 milliliters as our new volume. Now that we know the new volume and we know the number of moles of hydronium ion formed, we can determine its concentration. Because we want to find our concentration in moles per liter, we will need to convert the 60 milliliters to liters. We do that by dividing by 1,000, as there are 1,000 milliliters in a liter, allowing us to cancel the milliliter unit, leaving us with liters. When we plug this into the calculator, we get a final hydronium ion concentration equal to 0.0333 moles per liter. Now that we have the concentration of hydronium ion, we can finish the question by determining the pH. Our pH equation is to take the negative log of the concentration of hydronium ion. When we substitute in the value that we've determined here, we can solve for the pH. Plugging that logarithm, negative logarithm, into my calculator, I get a pH of 1.47. And that's the final solution. So let's go back and take a look at everything we've done. Initially, we have to do the reaction between hydrobromic acid and sodium hydroxide, as that's what's occurring in the titration. So, hydrobromic acid, aqueous, because it's in solution, plus sodium hydroxide, also aqueous, forming sodium bromide, a salt, along with water. In a strong acid, strong base titration, we will always form a salt and water. This is also known as a neutralization reaction. In my initial ICF table, I fill in my hydrobromic acid, sodium hydroxide, sodium bromide, and water. However, water can be ignored because we're in solution and it is in excess. My change in concentration is determined by my limiting reactant, sodium hydroxide, and I find a final molar amount of 0.002 moles of hydrobromic acid. I also have the formation of my salt. However, that salt will not affect pH, and therefore we do not need to consider it further. Those molar values, in case you forgot, needed to be determined using the initial concentration and the initial volume of the acid, as well as the initial concentration and initial volume of the strong base. Now that we had the total moles remaining of the acid, we formed a new ICF table where we looked at the reaction between hydrobromic acid and water. Again, remember that we don't have any sodium hydroxide left, so the hydrobromic acid in solution will react with the excess water that's also in that solution, forming hydronium ion and bromide ion. The bromide ion does not need to be considered because it does not affect the pH of the system. It came from a strong acid and is a negligible conjugate base. Therefore, in our initial value for hydrobromic acid, we fill in the 0.002 moles that we calculated in the first step. Because the reaction goes to completion and water is in excess, the hydrobromic acid is our limiting reactant and all of it is consumed, leaving us with 0 moles. We therefore form 0.002 moles of hydronium ion. Remember to check your stoichiometric ratios. In this example, it's 1 to 1, so we do not need to multiply this value. We then considered how our volume changed from the addition of sodium hydroxide. We added 40 milliliters of sodium hydroxide to 20 milliliters of hydrobromic acid for a new total volume of 60 milliliters. Knowing the volume and the number of moles of hydronium ion, we were able to solve for its concentration. We had to convert milliliters to liters so that we would solve in moles per liters. And we ended up with a final value of 0.0333 mole per liter. With that value, we were able to determine the pH using our pH equation, the negative log of the concentration of hydronium ion. Solving that negative logarithm, we got a value of 1.47. And that's how you take the pH of a strong acid, strong base titration before the equivalence point.